My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 478. In this lecture, I will continue my discussion on K-medoids. Before understanding this lecture, I request you to go through my previous lecture, that is lecture number 477. In lecture number 477, we were discussing that one of the popular algorithm for K-medoids is called partitioning around medoids, that is PAM, PAM, PAM. This is the algorithm just like Lloyd's algorithm for K-means. PAM is an algorithm for K-medoids. It's very similar to K-means with some differences. This is what we discussed at the end of lecture number 477. So we have same initialization. It is very similar to K-means with certain differences. You do the initialization again. We do the initialization again using the same ideas like K-means plus plus. Basically, you pick K points. Your initializations in K-means plus plus, what do you do? Using some probabilistic method, you pick K points from your dataset capital D as your initial centroids or initial medoids. Same thing, it is very similar to what you do with K-means plus plus. That is step number 1. In second step, what you do is assignment. I am just following the same method, same steps. What are the steps here? My first step is initialization, that is first step, isn't it? Next, assignment, third one update, and fourth one termination, isn't it? Fourth one is termination. And these are the 4 steps that we saw for all these 4 steps we saw for K-means, isn't it? Trying to follow the same method. Assignment again. What is this? Assignment again. The same thing. We use the closest medoid. Here we use the closest medoid method. We use proximity again. Closest in the sense proximity again. So given any point xi, it belongs to cluster Sj. Given xi belongs to Sj, if medoid Sj, let me say it is Sj. This is medoid Sj is the closest medoid to xi, isn't it? Same proximity method. This is same as K-means. No changes. I can say there is no changes, isn't it? Our third step was update or recompute centroids. Here there is a difference because in update stage in K-means, what did we do? In K-means, we said Cj equal to 1 by mod Sj xi sigma, xi belongs to Sj sigma xi. This is what we did in K-means. In K-medoids, we don't want to use mean approach. In K-medoid, we don't want to use this mean approach. This is what we did in K-means. In K-medoids, we don't want to use mean approach. In K-medoids, it changes slightly. This is the core idea of Pam algorithm, isn't it? What are the steps? You can say, let me say these are the points x1, x2, so on, x10. Swap each medoid with a non-medoid points. Here what we have to do? We have to swap, let me say, swap each medoid with a non-medoid points, non-medoid points, isn't it? Let's say we have x1, x2, so on, x10. Let's assume x1 and x6 are your medoids. Let me say my x1 is medoid 1 and x6 is medoid. This is your medoid 1. Which one is your medoid 1? This is your medoid 1, and this is your medoid 2. What does it mean? What is my k value here? My k value is 2, means k equal 2. K equal 2 means 2 medoid, isn't it? So it is a 2 medoid. It is a 2 medoid clustering. Let's assume x1 is your first medoid, x6 is your second medoid. Now what I am saying here is x2, x3, x4, x5. Just see, x2, x3, x4, x5 are non-medoid points. Similarly, x7, x8, x9, x10 are non-medoid points. Now make one of these non-medoid points as medoid, isn't it? Make one of these non-medoid points as medoid and make this medoid point as non-medoid point. That's what I mean by swap. Swap the medoid point with a non-medoid point. Now, when you swap it, what you have to check for is if your loss is here k equal to, after swapping, if your loss decreases, that's important, isn't it? What you have to check for after swapping, what you have to do? When you swap it, what you have to check for is if your loss decreases, keep the swap, else undo the swap. So a big question could be, what is the loss means? What is the loss function in k-means? What is the loss function in k-means? What is the loss minimization in k-means? What is that you are trying to minimize k-means? We are trying to minimize in mathematical objective. We are trying to minimize for each of your k clusters. Loss in k-means is sigma I equal to 1 to k, x belongs to Si, norm x minus mj whole square. Within each of your clusters, you are trying to minimize this, isn't it? What you are trying to do? You are trying to minimize. You are trying to minimize this, isn't it? By mj, what I mean here is mj is medoid j. You are trying to minimize your intercluster. You are trying to minimize intercluster distance. You are trying to minimize intercluster distances, isn't it? Intercluster distance, otherwise intercluster distance. This is your, what is this? This is your loss function. Which one is your loss function? In k-means, this is your loss function. So what you do here is, algorithmically speaking, you make, instead of m1 being your medoid, you swap it. Instead of m1 being your medoid, what you have to do? Just see. Let's assume I have x1 to points extend. Let's assume this is x1 is my medoid 1 and this x6 is medoid 2. So what I will do first is I will compute loss value. I will compute loss value x1 as my medoid 1, x1 equal to m1. I will compute loss value as x1 as my medoid 1, x6 as my medoid 2. Let's assume I will get a value of L1. Let me say I am getting, let me say this value is L1, isn't it? I will get a value of L1, some loss, isn't it? And the loss is computed using sigma I equal to 1 to k, xi belongs to Si, norm of x minus mj whole square. Mj means medoid j. Now what I will do here is I will swap a medoid point with a non-medoid point, isn't it? That is m1 equal to x2, m1 equal to x2. I will make m1 equal to x2. Just see, I am swapping this. This is important. Just see, I am swapping, isn't it? I will make m1 equal to x2. That's what I am saying. m1 equal to x2. I will make m1 equal to x2 and I will make x1 as non-medoid point, isn't it? That's important. My m2 remains same. My m2 remains x6 only. This is called swapping. In this case, what did I swap? I swapped. Which one we swapped? We swapped. What did I swap? I swapped x1. I swapped x1 and x2. What did we swap? We swapped like this, x1, x2. Isn't it? My x1 was my medoid 1. I swapped this. After swapping, compute the loss function. After swapping, compute the loss value again with m1 as x2, and m2 as x6. I have to compute my loss m1 equal to x2 and m2 equal to x6. We can always calculate loss. How can I calculate? Sigma I equal to 1 to k, xi belongs to x belongs to si. What is this mj? My medoid j. You have new medoid, your loss will change, isn't it? You have new medoid, your loss will change. Let's say this is my L2. Previous one is L1. Now let me say that is L2. If in the case of L2, for L2, what is your this one? M1 equal to x2, M2 equals x6. Now I am calculating L2. If loss L2 is less than L1, if loss L2 is less than L1, then I will say M1 equal to x2, M2 equal to x6. Else M1 equal to x1, M2 equal to x6. I will keep doing this. I will not leave with one swap. I will not leave with one swap, isn't it? Isn't it? Yes. Means for what? For I will check for x1, x3. I will check for x1, x4. Similarly, I will check for x6, x7, x6, x5. Isn't it? Lots of swaps that are possible. Isn't it? Lots of swaps are possible. Isn't it? I will redo this assignment depending on I will redo this assignment, isn't it? If swap is successful, when do I say swap is successful? When the loss value is less. If L2 is less than L1, swap is successful. Once swap is successful, you go back and reassign the points to the appropriate cluster. Means you have to go back and assign the points to the appropriate cluster. Means that is step 2. It's very similar to K-means, except that update. In your update, you have swap based scheme. In update, what you have? In the case of update, you have swap based scheme. This is swap based scheme. Instead of computing mean by formula, instead of computing mean, yes, here instead of this one, instead of calculating k means, now in this particular algorithm, that scheme is swap based scheme. Here swapping, isn't it? Swap based scheme, instead of computing mean by Cj equal to 1 by mod Sj, sigma xi belongs to Sj, sigma xi, isn't it? This algorithm is called partitioning around medoids. This swap based scheme algorithm is Pam algorithm, partitioning around medoids. A very popular algorithm for it's a very popular algorithm for K-medoids. Now one thing that you notice here is sigma I equal to 1 to k, sigma x belongs to xi, norm of x minus mj whole square. What is my mj? Mj is medoid, isn't it? Distance, what is this x? This particular term. What is this particular term? This one. This particular term is distance between xi comma mj. It is also a data point. Here what is this? This medoid mj is also a data point, isn't it? This is also mj is also data point. Since medoid is also a data point, what I can do is this my only thing that I need is distance between xi comma, I need distance between xi comma mj. Here furthermore your mj is a data point. If somebody gives you similarity value, if somebody gives you similarity value xi comma xj or distance value, similarity value or distance value for every pair of points, means for every xi comma xj belongs to d. D means data set, isn't it? This is like your kernel metric, isn't it? This is like your kernel metric in support vector missions, SVMs, because kernel metric is literally nothing but similarity metric between every pair of points. So somebody gives you similarity metric or kernel metrics, you can easily do K-medoids, because I will compute this part. Which part? This norm xi minus mj whole square, that is distance between xi and mj is a data point. The big advantage and the massive advantage of K-medoid is, of course, it makes life better because it is interpretable. K-medoid is interpretable, but additionally it lets us to have kernelization. Whenever somebody gives similarity metric or distance metric, you can immediately use it, norm xi minus mj whole square. You can replace it by distance between xi comma mj belongs to d. So K-medoids, in addition to making your results interpretable, helps us by making everything kernelized. So your standard k-means is not easily kernelized. Your K-medoid is easily kernelized, because in your standard k-means, your sigma I equal to 1 to k, x belongs to xj, norm x minus mj whole square. This mj in your in your k-means, this mj, it need not be a data point. Need not be a data point. Where in standard k-means, isn't it? In standard k-means, this mj, it need not be a data point because this is centroid. In such a case, you cannot kernelize easily. Of course, there are ways to kernelize k-means. I am not saying it is not possible, but K-medoid is much more. K-medoid, I can say K-medoid is much more. K-medoid is much more easy to kernelize. What is this? This is need not be a data point in the context of k-means, isn't it? Yes, K-medoid is much more easy to kernelize because as long as I have kernel metrics, it becomes trivial. That's a huge advantage that K-medoid provides in addition to the interpretability. I request all of you to go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.